station is on the miraculous Rollins NZ6A. Rob Rollins is a semi-retired electrical engineer from New Zealand, but is involved in teaching RF and selling part-time. The first part of his career was with New Zealand Telecom, and since 1989 with Hewlett-Packard, Agilent, Keysight test equipment in the SF Bay Area. Rob has a degree in electrical engineering from the University of Canterbury in Christchurch, New Zealand, and is a life member of IEEE. Rob has been licensed since 1963, when his first call sign was L3PAR, and he is interested in mountaintop operating, APRS, and public service events. Rob, the floor is yours.
This microphone's working on Zoom. It is? Okay, great. Well, thank you, folks. I'm going to sit down here and use this microphone. Can you hear me, guys? 1, 2, 3, 4, 5. Great. Well, this time, Larry bought me dinner. Thank you, Larry. Always happy to come and talk to you guys. I use your repeater system, and I'm very happy to pay back to the ham community. As Jan mentioned, I've been around for a while and gathered a lot of experience from Elmers all across the ham radio community, both in my home New Zealand and here in the United States. One of the things that I've learned as I've gone through my career, both in electrical engineering and also in ham radio, is that keeping it simple is the most important thing. And so many people will delve straight into a lot of minutiae that doesn't really get to the bottom of the reason why people would want to use, in this case, a VNA. So most people know it's something to do with antennas, maybe not. Some people think it's a spectrum analyzer. Some people think it's not. Who amongst you has professionally used a VNA in their careers? Who's used a VNA in their jobs? So I'm speaking to a group of relatively new people to VNAs. Is that correct? Okay. I'm going to sit down and start the presentation. This has been incredibly challenging for us because we're trying to run Zoom as well as run the live. How's it going there, Mike? Is the voice okay? Okay. So RF test, radio frequency test, is a important subject for me, in part because I teach it at Sonoma State University in Rohnert Park in Sonoma County. And RF test is interesting because radio waves and their electrical equivalents are actually a perfect example of physics in practice. Mostly antennas behave the way they should, except they don't some of the time. And when they don't, that's when test becomes important. Now, all of us here have at least tested SWR on some kind of antenna. Who's tested SWR on an antenna they've either bought or made? Okay, what did you use to test the SWR? I'm sorry? What instrument did you use? Antenna. Okay, so was it a one you built yourself or one you bought? MFJ. Okay, MFJ antenna tester. I have one of those. The 259, I think it's called. Yeah. And what is the figure of merit that you get from the MFJ 259 when you test your antenna? What's the measurement making? Anybody want to help him? The measurement you're making when you use an antenna tester on an antenna, what's the measurement you're looking for? SWR, standing wave ratio. Okay? So standing wave ratio is something we all talk about. We talk about it at it without necessarily understanding exactly what it is. But the MFJ 259 does two things. Firstly, it tells you what the SWR is, but it also, what's up?
He unmuted his hand, so please go ahead.
No audio.
There's another guy. Okay, go ahead.
Okay, so we make a measurement on our antenna and we measure an SWR of 1.4 to 1. The MFJ 259 gives you something else that's very important. So, Rich, do you know what the extra information is with the 259? And one more important thing. Okay, impedance. And impedance is resistance and reactance. So the important thing about the MFJ 259, it gives you the scalar number, the single number of, say, 1.4 to 1 SWR. But it also tells you that your antenna is 50.6 ohms plus J20 or minus J20. And depending on whether it's plus or minus, that means the antenna is inductive or not. So the MFJ 259, which costs $180 something, is actually a vector network analyzer, because it's actually looking at the impedance at the SO239 at the top of the instrument, and it's actually telling you what R plus JX is. So a common concern people have is the difference between a network analyzer and a spectrum analyzer. So let's sweep this one out of the way first before we get too confused. The spectrum analyzer looks at signals. A network analyzer looks at components. So simply, a network analyzer looks at a device by sending some energy to it and looking at the response. So it's a stimulus response device. So as in Richard's example here, where you're looking at your antenna, you're shooting a signal up from the MFJ 259 into the antenna and looking at the response. So a network analyzer creates a stimulus and compares it to a response. And reflections on an antenna feed line are a classic example. A spectrum analyzer only looks at a response. And those of you who will be interested, this is a spectrum analyzer very similar to the Nano VNA. Costs $50 from you know where. And I'm going to pass it around. You guys can play with it. This is but before I pass it to you, Jan, this is really a glorified, yeah, I want it back too. This is a glorified radio receiver, okay? But the thing it does, it has more sophistication than your regular Baofeng or whatever. It's got a screen, for instance, displays frequency versus amplitude and so on. But the point is, the spectrum analyzer is a measuring device that measures signals. So a spectrum analyzer only looks at that response, either signals from the antenna or the output from a radio. Now, those of you who've been to Pacificon over the years have probably seen the ARRL table, where they have a spectrum analyzer. You turn up with your HT, you key it up, and they tell you what your harmonics are like. What's your third harmonic supposed to be to meet the FCC standards at 144? Well, it's actually not quite as bad as that. It's in the 40s, I think. It depends on your power. But the radios that a lot of us use, the Baofeng radios that cost $20, typically the harmonic is not dB down. It's usually about 5 dB down. So a spectrum analyzer can be used to determine how clean a transmitter signal is. So I'm not going to talk any more about spectrum analyzers. I just want to make sure you clearly understand the difference. Now, there are very few network analyzers that are both. And this is a Keysight FieldFox. And this is what I sell. I sell this for my living. And these are combined spectrum analyzer and network analyzer. And this thing I'm holding here probably costs about 60K. Okay? So this is not something you want to, leave randomly around. I'm always really, what was that? So for instance, I'm always careful where I park when I have this in the car, because I don't want Larry to sneak around behind me and break into my car and steal it. So the important thing about this device is it's been designed by one of the leaders in test measurement, Keysight, who I used to work for. And it's been designed with 2 instruments in one. In fact, it's about 18 instruments in one if you want to go into it. But this is not the usual instrument that you will buy from Siglent or anyone that makes relatively low-cost spectrum analyzers. Now, the big difference that you're going to call me up on, though, is what about tracking generators? So if you buy a Siglent, now I've managed to, is that coming, that's not on the screen, is it? Okay, so it's possible to get a tracking generator for a Siglent spectrum analyzer. So the tracking generator is an oscillator that tunes with the spectrum analyzer. So if you tune your spectrum analyzer to 144 megahertz, it will transmit at 144 megahertz, and you can use it to measure scalar quantities like insertion loss. So it doesn't do vector measurements. It's actually enough for a lot of what we need. And as I said, the Siglent and some of the low-cost spectrum analyzers include tracking generators. But that's not a vector analyzer. So what I'm talking about today is the Nano VNA. The Nano VNA originated in China, like a lot of things these days, and has come on the market and created quite a storm, I think, amongst not just the ham radio community, but other people as well. To give an example, I teach a class at Sonoma State on RF tests. And during the pandemic, the university professors were not prepared to allow the field box units they usually use to be sent to people's homes. So what do? They bought a whole bunch of these Nano VNAs. And this Nano VNA is functionally equivalent to the $60,000 Keysight field box. Functionally equivalent. Makes most of the same measurements. Doesn't do it as well, but in terms of teaching, for teaching the students, this was ideal because they had this in their home and they were able to play with it as long as they wanted to. They weren't restricted with lab time. And we had classes that taught them how to measure insertion loss and return loss and all that cool stuff. How many people have already bought the Nano VNA? I think Rod. Okay. How many people have actually turned it on?
Audio went.
Yeah, it did. I think they're working on it.
Take the wire, no. I just moved the tabs just to see if you're awake. Okay, so the Nano VNA was put together by a group of Chinese engineers, whether there's whether children's tidy hands were involved in the manufacture or not is something we possibly should consider. But the point is, it's on the market at prices varying between $55 and $150. And you sort of get what you pay for. The one I've got here is actually 2 years old. It's got a 2.8-inch screen. There's a 4.3-inch screen now. Oh, shoot. We spent about 2 hours setting everything up here today, and I think I'm hosed in one department. One of the problems with these modern computers with their with their USB-C connections is there's only 2 USB-C connections and it's used for everything, and I needed about 4 of them. Excuse me? Is it working? Yeah. So the more expensive versions have the bigger screen, which is good for those of us who've got bad eyesight. You can get a version that has a metal case. The one I have here happens to have a 3D printed case I bought from eBay just to protect the device. It also has a bigger battery. Some people have bought the units that have the end connectors pre-adapted. So basically the VNA is encased within a metal container with a number with extensions of the SMA connectors out to end connectors. And those of you who are in the business know the end connector is so much more reliable and repeatable. The SMA connector is really not supposed to be used more than 100 measurements. Functionally identical to the more expensive VNAs, but frequency range is less. So I think the frequency range on this one goes to, I think, 900 megahertz. But you can buy them that go 1500 or 400 megahertz, different versions of the same essential product. And you can see here, I've just shown a couple of the Amazon adverts. I don't particularly favor Amazon, except it's very easy to return stuff for Amazon. And just as I was driving over here, I returned something by going to my local UPS and just handing it over, and they took care of it. I didn't have to worry about it. And I've already got the credit. So not trying to push Amazon, there's other vendors that do the same thing. But when you're buying stuff like this, it's nice to know that you can return it if it doesn't work or you don't like it. The key features that you still have are the ability to do Smith charts. And we're going to talk quite a lot about Smith charts tonight. We have calibration to remove the effective cable. We have an offline PC app to allow you to document the measurements. And you can actually make time domain measurements. So I'll not talk about that tonight. Has anyone ever made time domain measurements on cables? You know what I'm talking about? Give you an example. A guy came into our local radio club and he said, the radio on my yacht doesn't work. I said, oh, that's interesting. Why not? He said, well, I took it to the local fitter over in Alameda, and he put new spreader lights in, and after I came back, the radio doesn't work. I said, oh, this is interesting. So I actually hopped in my car and went over and had a look at his boat. And the Keysight box has quite a nice TDR function. And I was able to fire up the time to reflectometer functionality here and say your problem is 20 foot up the mast. So you got up the tape, and sure enough, that's where the spreaders were. So basically, the people who put the spreaders in had put a drill through the cable and had a dead short at that point. So TDR functionality gives you the ability to look at cable, determine whether it's good or bad, and if it's bad, where it's bad. A classic example again, our repeaters in Mill Valley, not above Mill Valley, we've got a real problem with old cabling. And we can see, even though it's heliax coax, we can see the impedance discontinuities all the way from the repeater out the antenna. And it was not good. There's a lot of reflections in there, a lot of what was probably wet coax that was, wet heliax in this case, was impairing the performance of the repeaters because of the cable. So that's a feature that's in all VNAs, although, to be honest, it's very difficult to use in the nano VNA, and I wouldn't promote it. A little bit of definition, I'm afraid. I don't like to put too much in here, but the S parameters are the way you can describe a device entirely at a particular frequency. So the four S parameters, S11, S21, S22, and S12, if you know their values in amplitude and phase, you can determine the way a device will perform. So this is of academic interest to you, in part because the nano-VNA doesn't even measure two of the parameters. It only measures the reflection and the insertion loss. But if you get into the minutiae of VNA technology, these four parameters are key to defining an amplifier or a filter or a piece of cable or any component in your RF chain can be described by these parameters. And this is the model. Again, this is matrix technology, matrix manipulation from high school. But the important thing I want you to understand here is the S parameters are small signal S parameters. They are the performance of the device, whether it's a filter or a coupler or whatever, when it's not going into saturation. If it's an amplifier, there's only a certain limit to how much signal you can put in before it starts distorting, and it's called gain compression. So just remember the S parameters that you measure with the nano-VNA are just the first two and the most important ones. Let's look at some devices you can measure. So you can measure a load. And what was the question? I'm not? Last time I did that, it stopped working on me. Okay, so thank you for telling me that on current site. But Mike, you have to tell me if it's still going out on the web, on the Zoom. Does that look okay on the Zoom? Okay, sorry about that. Thanks for reminding me. Yeah, I often miss that. So a load could be an SMA device. Either I dropped or mine, but here's an SMA load. It's a standard SMA device. You probably all got them, picked them up somewhere. And when you buy the nano-VNA, you get loads and shorts and open them with it so you can calibration. The short is exactly what it looks like. So you can see the center pin here is connected with a solid piece of brass to the outer. And another one-pointed device, of course, would be an antenna. The antenna that you buy at Pacificon, is that an advert that will give me credit, Larry? Am I able to give Pacificon credit for selling me cheap antennas? What's that? I'll tell you. Okay. We'll talk about it later. Now, the big difference between the nano-VNA and the MFJ259, which we discussed earlier, is the MFJ259 does not have a source. Unless I haven't used mine for a while, I don't think it has a source. So if you want to measure a piece of coax, you've got to have some kind of signal generator or something. To measure any two-port device, you need to have a transmit and a receive port. So if you want to measure a coaxial cable, an amplifier, or a filter, you need a two-port device. And this is where the nano-VNA comes into its own, because here you are for 50 or 60 bucks. You can have a two-port device that can characterize filters and coax in your own home or in your own car if you're so inclined. S parameters assume a characteristic impedance, and in our world it's 50 ohms. So the first S parameter that we care about is 1,1, and it's a measure of how closely the impedance of what we're measuring matches Z0. So when you're actually looking at the antenna, you're hoping to have it as close as possible to 50 ohms, and the distance between 50 ohms and where it actually is related to the SWR. The SWR value tells you how good the match is. So if the SWR is 1-to-1, you've got a very close match. Good luck finding an antenna that has 1-to-1, but that's another issue. 75 ohms is used in video and cable TV for various reasons. A perfect match has infinite loss. So infinite return loss. And I've already lost the load I just had. Too much stuff. But here's a load. So this load here, if you connect this up to your MFJ259, it will have an SWR of 1 to 1. If you connect it up to your rig and key up, the rig will be very happy. It will see a nice clean SWR, and until the resistor in here burns it out, you've got a perfect device. How far are you going to get with your signal that's going into just a load like this? Nowhere, obviously. So a perfect SWR isn't necessarily a solution to your problem. If you've got an antenna with a perfect SWR, you're in clover. If you're dealing with real antennas with real impedance, you're not going to get a perfect SWR. Now, we have an argument in our Marin Club about what a good SWR is for 2 meters. And if you take a stock diamond X50 or X100 antenna, stick it up on your and feed it with 50 feet of LMR or even 25 feet of LMR, you should get an SWR about 1.1 to 1. If you're getting more than that, there's something wrong. And I've got friends in Marin who disagree with me. They say, well, I'm getting out just fine. Sure, you'll get out, but maybe 2/3 of your power is being reflected back into the radio. Now that's bad for the radio, perhaps, because you're creating high voltage in the final stages of the radio. And it's also inefficient. So it's really worth focusing on getting your SWR down as low as possible. And we'll talk a little bit more about that. A VLA has directional couplers, and I'm not going to go into the minutiae of how directional couplers work. Basically, as I've already mentioned, you have a source, and you send that source in through a directional coupler to your device you're testing. So it's a filter in this case, or a piece of coax. The incident signal is being measured here, and the reflected signal is being measured. The difference between the incident signal and the reflected signal is called return loss. And return loss and SWR are different names for the same thing. Different quantities, but a high return loss is good. A high SWR is bad. But there's a 1-to-1 correlation between return loss and SWR, and I'll talk about that in a minute. If you're measuring insertion loss, then the incident signal that comes into your device under test, which might be a filter, and the transmitted, just subtract the two, and that's the insertion loss. So pretty simple. If you're trying to work out how much gain an amplifier has, you can use a VNA to do that. So I keep talking about return loss because return loss is very simple to understand, and in EE that tends to be what people talk about rather than SWR. Return loss is simply the difference in dB between the forward and reflected path. So higher return loss means better signal. Move this out of the way. Higher return loss is good. Means you've got lower SWR, and there's 1-1 mapping between SWR and return loss. So 20 dB of return loss, which is about what you'd expect to see is an SWR of 1.22. And this means 1% of your power is reflected. In this table, you can see the comparison of SWR and return loss. By the way, I'll be sending out these slides. See, you don't need to copy them. I'll be sending out PDFs of the slides. So we can see that a SWR of, we need the lights on? We're having a light show, are we? An SWR of 1.9 is a return loss of 10 dB, and 90% of your power is going up the spout and 10% is coming back. Do you want that? Do you want, if you've got a 100-watt transmitter, do you want 10 watts floating around inside your finals? It shouldn't be there and causing excessive voltage. So SWR limitation in our rigs. Most of our HF rigs, if our SWR is greater than 2 to 1, power gets cut back, gets rolled back. So managing your impedance of your feed line and your antenna and so on is part of the trick of surviving, not just in VHF, but also in HF. So voltage standing wave ratio isn't easy to understand. Basically, if you've got a standing wave, that means you've got some reflection, and the difference between the peak and the peak here and the trough is the standing wave ratio. If you've got no standing wave, then it's 1:1. And I'm not going to go into this in more detail because it's not straightforward. A simple animation as to how SWR corresponds to return loss. Just remember they're the same thing. Any questions, Mike, that I can answer before I move on? Okay, cool. So we're going to only make 3 measurements today. Remember at the start, I said I'm going to go simple. I don't want to go complicated. There's a whole lot of stuff to go into for you guys into next week. So the first thing I'm going to do is I'm going to plot antenna match on this wonderful piece of Pacificon antenna. And I'm going to do it over a desired frequency. Either going to measure this wire or return loss. You can choose whichever you want to. But remember, there's no guarantee to radiation performance. So a dummy load is perfect. A real antenna is not perfect, but at least it radiates to some point. We're also going to measure antenna impedance, and we're actually going to look at the real and imaginary parts of that antenna impedance. In other words, the real resistance and the reactance. And perfect antennas usually react to some degree. They're either inductive or capacitive. Does anybody have a 43-foot vertical? Anyone, HF mavens, have 43-foot vertical? Anyway, 43-foot verticals seems a funny number, but it's a number that actually allows you to build a multi-band vertical with surprising performance over most of the HF bands. However, the 43-volt vertical has significant inductive reactance. How do you fix inductive reactance? Excessive inductive reactance, what do you do to compensate? What's that? A what? Capacitor. Yeah, you put a capacitor in. So there's an excellent article in QEX magazine. Those of you who are interested, QEX magazine, published by ARRL, has all the geeky stuff that doesn't make it to QST. There's a wonderful article about a year ago in which a guy was building a 43-foot vertical, and he used a network analyzer to determine what size capacitor he needed to put in series. And he built the capacitor himself because it had, I think it was like, 28 puff or something like that. And he built it himself because it had to work at kilowatt voltages. So some pretty interesting stuff you can do with R plus JX once you've... And I don't have a graphic, unfortunately. I wish I did. But 4 different values of R plus JX can have the same SWR. So you can have positive or negative reactance, in other words, inductive or capacitive. And it can either be above 75 ohms, above 50 ohms, or below 50 ohms, and you can still have the same SWR in 4 different scenarios. So SWR doesn't really give you an indication of what's going on. You have to delve into the real and imaginary parts of the impedance in order to determine what's going on. This is where the Smith chart comes in. How many of you have dealt with Smith charts? It's a bit esoteric, but the Smith chart has been around for a long time. It was around a long time before we had computers, and it was a slide rule, basically. When I was at university, we didn't have my nano VNA's flat now. Oh dear. We didn't have computers at university when I was doing this stuff, so everything we did was graphical, and we're basically using slide rules and protractors to use to play with Smith charts. The Smith chart is built into the nano VNA. It's a key feature, I think, of understanding our area. And we can measure insertion loss of a filter or a cable over a frequency range. Now, what's really important with any device, any network analyzer device, is that as soon as you attach cables to your device, you've screwed up your calibration. And every network analyzer has capability to calibrate itself to remove the effects of cables. Because if I'm going to characterize this filter here, here's a little strip line filter for 2 meters. If I'm going to characterize this filter and attach a couple of cables to it, by the time I attach the cables to the filter and attach to the VNA, I'm already, how long is that? It's not a quarter wave, but it's about a about a fifth of the wavelength at 2 meters away from the VNA. So already you've got phase shifts along the cable, even though there's only like an 8-inch cable. So the ability to calibrate out the effect of connectors and cables is crucial for any measurement you make with the VNA. One of the big things about the SMA connector, I mentioned earlier, some people have N connectors on their nano VNAs. And if you're going to use the nano VNA in anger, I highly recommend you buy conversions with the N connectors. Because N connectors, I'm sure most of you have seen an N connector, but an N connector is built like a battleship. An N connector works up to 18 gigahertz and is able to handle strain that you cannot possibly handle on an SMA connector. SMA connectors are designed for less than 100 insertions. So if you make more than 100 insertions on this, you can no longer guarantee the performance of SMA. And that depends on the price of the SMA you're buying. So for that purpose, we use connector savers. And you can see what I've got here on the 2 ports of my nano VNA. I've put in male-female connector savers. And these connector savers, obviously, they add to the, I have to calibrate for them because they are real devices. I have to calibrate now. And you can buy these cheaply from you-know-where. So what we're going to do now is we're going to have a look at the standing wave ratio of a dummy load. So the dummy load, I've done it again. This is a SMA 50 ohm dummy load. And it's 50 ohms plus or minus whatever, depending on how much money you pay for it. And I wouldn't try and put too much power into it because I think you could cook it pretty easily. Unfortunately, we're not going to do quite as much video display as I'd hoped. I've got an external camera here which is connected into Zoom. So are you seeing it there at the moment, Mike? No, that's because I disconnected it. That's why. Okay. Try again, see if it comes in. It should come up under my name. You seeing anything? What's that? I can't understand what you're saying. Sorry. I just can't hear what you're saying. I'm sorry, Mike. You're seeing that, but it's not coming in on. Yeah, yeah. You've noticed my computer upgraded itself to Windows 11 yesterday. Just about fell over backwards when it happened. You've got to be careful if you deal with early adopter versions of Windows. You end up upgrading without even knowing it. This is not going to be great because I can't show everybody. At least, Jan, could you move that projector around? So at least here we have a camera that shows the, once it decides to focus, not you, it's my camera here. It's point and shoot cameras don't always focus when they should. Oh, look at that. So the Nano VNA has a really funky user interface. That's the only way to describe it. It has a little rocker here that you can use to adjust what you're seeing on the screen. And what I'm going to do now, I'm just going to take it away now, and I've got it adjusted for measuring, as I already, shoot, I know, that's problems. It's Windows 11. It's more important that I don't lose this. So I'm going to go back to plugging in the battery. Sorry guys, this turned out to be not straightforward. Okay, well at least we got the presentation. So my dummy load in this picture is attached to channel 0. So you see this SWR measurement is 1-to-1 across the whole band here, which is, it's hard for you to see it, but it's 144 to 148 megahertz, so across the 2-meter band. So obviously the dummy load here is good for 2 meters. Here's an antenna. Yeah, thanks. Yeah, it's not really good. So here's an antenna in my living room. I think it was actually this fine Pacificon one too. And so basically, here's the SWI measure across 9-to-1 here and up to 3-4-to-1 over here. So it's not 50 ohms. All right. How many people have bought Alfang, taken the antenna that's on it, thrown it away, and attached one of these? Thought you're doing yourself a favor? Not necessarily. Some of the measurements of some Alfang antennas show that they're actually better than you might expect. But then the whole other issue of Alfangs, which of course we all know only too well. So I think it was Roger, was it, that wanted to measure an SWR antenna? Was it Roger? Anyway, so if you want to measure an SWR antenna here, here's what you do: you attach it to port 0, and you set up the antenna, the VNA, to make a measurement of SWR versus frequency. Now, there's 2 ways you can do this. You can do it through the front panel, through the funky old front panel here, with its rocker switch, or you can do it through an external PC program. And in this case, the PC program is called VNA Saver. And VNA Saver allows you to make measurements on the VNA Saver in a quite professional way and document them. And what I'm going to do is I'm going to pass around an example of a measurement I made on, this is a Yaesu antenna, believe it or not. This is a Yaesu antenna off one of my Japanese rigs, and it shows the SWR of this antenna on the 2-meter band, and at 144 megahertz, it was about 3-to-1, and by the time it got to 148, it was about 8-to-1. And this is a Yaesu antenna, so you don't get what you pay for necessarily. So in here in that plastic bag, there's a plot that I did on VNA, and the antenna is sitting there at the bottom. So paying a lot of money for an antenna doesn't necessarily give you anything better. Here's where the VNA, the nano VNA, can help you decide what's actually going on with antennas rather than just blindly following what's said on the spec. So the Smith chart was invented before computers. So way back in the 20s, and there was a guy in the States and a guy in Japan invented the Smith chart at the same time. And all it is a plot of complex impedances. It's a plot of complex impedance versus frequency. So the bullseye at the center here is a termination that has a 50 ohm impedance, and the circles around here are equal to SWR. So the first circle is 1.1, second one is 1.5, sorry, 1.2, 1.5, 2.0, 3.0 SWR. So depending on where your antenna falls, you can measure your SWR instantly just by looking at it. So you can connect up the nano VNA to your antenna and put it in Smith chart mode, and immediately you can tell whether the antenna is any good or not. How cool is that? And you can compare 2 antennas. You can go to the desk at Pacificon. You can go through all the antennas and compare them. Hey, Larry. So the bullseye is 50 ohms, and the circles around the bullseye are the constant SWR. So I'm just now going to put on the SWR trace here. That's going to be very hard for you to see, I know. But Jan, is it readable? Not very well. Not lot. Yeah, I should have done something. I don't know what it is. So, if you look at this, you might think, "Oh, this is perfect SWR. It's right on the bullseye." Well, I've got bad news for you. I hadn't calibrated this first, and by the time you calibrate it, you end up with a plot much like the one that I'm passing around. So, a real problem for any of us, and I'm the worst offender here. Don't just take the nano VNA out of the box and start using it without calibrating, because you're measuring. What are you measuring? You're measuring a device that happened to be in a particular state last time it was used. It was perhaps used for measuring a length of cable or something. Everybody in the RF community knows this. Calibrate first before you make any measurements. Any questions on this chart, because it's super important. It's super easy to use, and it gives you visibility you don't have any other way in managing impedance of your devices. Okay, here's the antenna at 146.1. So you can see I just used it at one frequency. 146.1 is the input into our simulcast system in Marin. And you can see it's way outside the 3-to-1 circle. So if it was here, it would be 1 to 1, 1.2, 1.5, 3 to 1. And so it's outside the circle. It's slightly inductive. Does that matter? No, because our HDs are designed to work with these crappy antennas. I mean, they ship with them. So I can't actually remember which antenna this was. But the antenna is close to the this is resistive plane here, and this is the inductive plane. This is resistance up here, and this is capacitance down here. So you could perhaps compensate. I mean, how do you fit a series capacitor at the bottom of a SMA antenna? It's unlikely you're going to do that. But on HF, this is much more practical. So you've got your 43-foot vertical. Well, the guy on the front cover of QSD with all his coffee cans, did you see that? All the LE cans. If he had a slight reactance remaining in the antenna at, I think it was 15 meters he had it tuned up for, he could have tuned that out by putting in a series capacitor or a series inductor, depending on which way it went. So here's a sweep of the antenna from 100 to 200 megs. So ironically, the SWR is better at 200 megs than it is at 2 meters. So here's 2 meters over here. Here's 106.1, which is the frequency we want to be efficient at in Marin. But obviously, you can see that it goes all over the place. And by the time you get to 200 megs, it's getting closer to the bullseye. But, you know, antennas are a black art. And maybe it works just fine. And maybe it just happens to match the output stage of the rig you're using. And on that issue, the Meltangs, in my opinion, have a output which is nothing like 50 ohms. They are actually designed to work with their rubber duckies that come with them. So the rubber duckies and Baofeng transmitters are matched together. It's my supposition. I can't prove it totally, but my observation is that most Baofengs work better with the antenna that came from the shop, than adding on an external antenna. If you look at a resistor and a capacitor in series, you will see here, this is like, I can't remember exactly what the resistor was. I think it was a 50 ohm resistor and a small capacitor. So as you sweep it over frequency, you can see at high frequency, it's close to 50 ohms. But as you go to lower frequencies, the reactance of the capacitor becomes higher at lower frequencies, and it becomes further away from 50 ohms. If you've got an inductor and a capacitor, like a tuned circuit, you can actually determine where your tuned circuit is actually going to resonate by looking at the Smith chart. Cool stuff. All right. It looks like it's not going to be practical for me to do the measurements, but we'll just walk through the process here. And as I said to you 10 minutes ago, I'll be happy to PDF these slides out to you, and you can share them amongst the club. Nothing proprietary here. So the first thing I'm going to do now is I'm going to do a two-port measurement. And the device I'm measuring here is a bandpass filter made by Solar Networks. Summit's on the air, people. Oh, here it is. It's in my plastic bag. It's a 2-meter bandpass filter, and it's designed to stop intermod and various other overloads occurring when you're out of the field with a portable rig. Okay, you can't really stick it between your HT and your antenna, but if you've got a mobile rig, you can put it in between and reduce the effect of the single FM station and so on. So in this case, the first thing you have to do is you have to determine the effect of the cables, and this is the calibration process. So you take the 2 cables that come with it. It comes with these 2 black cables and a barrel connector, which it also comes with, and you do a calibration on that test system. And as you can see, there's a bit of a droop in here. When you calibrate it, it takes the droop out. I don't have a picture of it, unfortunately, but once you do the calibration process, that becomes a flat line. And this is 134 to 148 megahertz, just on 2 meters. So you can see, without the calibration, there's almost half a dB of droop there. So by doing the calibration, you get rid of the droop, okay? And when you put the filter in, instead of the barrel, hey-ho, there's the bandpass response of this 2-meter filter. So as you can see, it's got some quite steep stop bands down to about, it says 70 dB. It's hard to believe that you can actually do that with this device. I'll be reluctant to believe much more than 50, but it's more implying that you can get down to about 70 dB of attenuation off band. So if you're trying to get rid of a satellite signal or a cellular signal or a pager signal, these stop bands are very useful to stop your radio getting zapped. So here's the filter and its response. Pass it around. Thanks, Jan. And there's lots of filter designs out there. There's one here, a strip line filter. This is a little 2-meter filter by off eBay. The advantage this has under the bottom filter there is you can run 100 watts through this thing. You can't run 100 watts through this pad, or you end up with mangled plastic. So one of the big things, quite a lot of you, I'm sure, have got the SDR radios, the low-cost $20 dongles, whatever you want to call them. And the big problem with the SDR dongles is they're only 8-bit A to Ds, and they overload very badly. What causes overload for a SDR receiver typically? FM transmitter. So there's a class of filters that you can buy that are designed to basically remove the FM stations. And this is my last example. I'm going to pass it around again. It's a band reject filter. It's designed to reject 88 to 108 megahertz. So you can fire up your SDR radio without having your local top 40 station blast you out of distance. So I've shown you 3 different types of measurements. Measuring, first of all, just SWR. Secondly, SWR, R plus JX, the actual resistance and reactance combined to create the impedance. And then we've talked about making 2-port measurements. It just easy being a length of cable that I was measuring here. But as I mentioned, you need to calibrate first. So you put a barrel in place and then run a calibration routine. Otherwise, you're dealing with insertion losses of cables and other unknown measurement errors. And then you just take the barrel out and put in your filter or whatever it is. I've been playing with, I don't know about you, but my junk box probably has about 30 crystals of various frequencies. And what frequency are they? Good luck if you can read the embossed frequency on the top crystal. It may not even be there. It might be a surface mount component. So you can actually very quickly determine the frequency of a crystal by connecting it up to the port 1 of a nano VNA. and it will give you this plot showing you the way the phase and the amplitude changes. So you see the very steep suck out here at the resonant frequency. A very quick way to characterize the crystal. Some of you may be aware that if you get maybe 5 or 6 crystals that are very close in frequency, you make a nice ladder filter and characterize it together by loading up different capacitances. So that's all I'm going to cover here. It's been interesting trying to make the hybrid thing work. I appreciate your help, Mike and Mike, to try and make it work. I think we've done the best, and Jan, we've tried to do the best we can for everybody. There's a lot of information about the nano-VNA. There's a nano-VNA users group, which has information every hour, it seems, on the nano-VNA, and talks about the upgrades and so on that you can take. There's a guide to the nano-VNA on Amazon Kindle. So this is a Kindle book that tells you how to use VNA. So if you're still mystified after tonight, which I'm sure you will be, at least you're hearing it for the second time. This will give you the third time. You can look at the Kindle book and see how you might use the VNA. QSC has done a couple of reviews. There was a review in March of 2020 on the Nano VNA. There was also a more thorough analysis in QEX magazine. And you can look through the literature. There's a tremendous amount of information in your hands as well. The key thing about the Nano VNA is it's not a simple device to use. You've got to have your wits about you to make sure you're not being fooled by things not being calibrated. And I hope I've given you a little bit of a taste of how much fun you can have and how much you can learn too. And the students that I had the last semester, I always say at the start of the semester, look guys, I know that you've heard the sirens call of software and you all want to be software engineers, but will you pledge to me that when you graduate, in this case, in their final semester of their undergraduate degree, that you'll go and work in RF rather than going into software? Because to be honest, RF is not sexy. A lot of people in RF are grey-haired like me and are moving into different parts of their lives. And there's a lot of money being made in RF tests. I'll give you an example. A customer of mine in Petaluma was an RF test engineer who was earning about 90K in Petaluma. Went to Facebook. He got 250K for walking in the door. Just for walking in the door, because he knew how to do RF, he knew how to build RF test systems. So an RF test engineer typically will build an RF test system for some kind of device, whatever it is. They'll build this system, then they'll have to go to the contract manufacturer, which would be in Thailand or China or Mexico somewhere, have to go and build the thing and maintain it. And these guys are really short on the ground. The big companies are paying big money. Mike's looking at his watch, so it might be time for us to wrap it up. So, questions? It's not working for everybody. So, Mike, what have you got?
The raise hand icon under the reactions button in your command
bar. I can't
bar,
hear you. I can't hear you.
type your name in the chat.
Okay. Yes.
Troy Amazon. Oh, hello. Okay. I went out yesterday just to see, and they had about 3 of them. Which one would you recommend?
Well, that's the problem. And Larry asked me to give a recommendation. Remember I said, Amazon will return anything. And so it's caveat emptor. Have a look at the specs, see what looks good, look at the reviews. The one I have used to 55 now. They're all much, you pretty much get what you pay for. I don't think there's anything bad. And I'd be a bit more dubious going to any of the Chinese vendors because you don't have the same return capability. So, yeah. I mean, if you want the bigger battery, if you want the bigger screen, which is good for most of us because we've got little eyes, bad eyes, go to the big screen or go to the end connectors. Yeah, you've got, which one do you have?
Yeah.
So,
It's the 4.5 inch.
and does it have in connectors? I'd have a look. Pass it around. That's probably a good idea. Yeah, sure. If in connectors. Yeah, yeah. So some of them have got a extension of the SMA connectors onto an end. SMA. Yeah. Pass it around.
I'm just going to pass it around. Pass it around.
So don't be frightened of it. The thing is, just go ahead and buy one. You're out $55 or $80 or $150. Play with it. See what you can find out. You might be amazed. Is there a question there? Yeah. Sure.
And I've had it for about 2 years now.
Okay.
How often do you have to get the firmware upgraded, and is it easy to do that? I've never done it. And number 2, how often do you have to calibrate it, and how long does it hold the calibration?
Okay. Good question. Can I answer the second one first? The calibration isn't like you might expect for a multimeter or another instrument where you're actually trying to deal with systemic deterioration of the product. The calibration is actually because every time you connect the device up, you've got different connecting to, and you're calibrating out the physical extensions of connectors rather than calibrating the measurement system. A device like this doesn't have calibration like you have for a multimeter or some device like that. Okay. And your first question I've forgotten already. Oh, firmware upgrades. I did one on mine. I can't say it was fun. It was a bit nerve-wracking. I thought about doing one before tonight. I thought, sure as eggs there, it'll screw up. I won't have anything working tonight. There's a process called DFU. Have you seen that on the menu? DFU. Yeah, it's an option on the menu. So if you go into the DFU menu, and then you can go through the firmware upgrade. But it's not something you do half an hour before a presentation. Yeah, this fantastic stuff on groups.io. The interesting thing is about this little spectrum analyzer that you all saw that I handed around. This is actually built in China but supported in Europe. And the cool thing about this is that there's a guy called Eric Kashruk or something like that. I think he's in Belgium or Holland or somewhere. And he's actually very good on the group that is designed for the spectrum analyzer. And there's some fantastic information on the groups.io for the
Yes.
spectrum analyzer. This is just called the Tiny SA, $50 at anywhere.
Rob, that's the one that comes in the brown box.
It comes better than the brown box.
Brown and gold.
Oh yeah, it is sort of brown. It's actually quite a nice little box.
Yeah.
Like that one.
Yeah, that's
Tiny SA. $50. So the cool thing about this is if you want to have the harmonic of your HT, you could use this, except one thing. It's not very good above 350 megahertz. So the third harmonic, so obviously that's not going to help you. You need something a bit flasher if you look for harmonics that go up there. But this has some other great things as well. And I, again, like you're saying, I urge you to have a look at the groups.io and see the stuff that's going on. And for $50, you have a lot of fun. Everyone's bored. Yes. Sure.
You had said something about you can only attach a lead 100 times and then it goes bananas.
Yeah, these connectors basically are not very good.
What was this thing you said we should stick in between and
It's called a connector saver.
connector saver?
Yeah, but basically it's in the presentation. But I mean, I've actually talked these on quite well so they don't come off. But it's just a male and a female. And pass it up. It's just a male and a female that's there. Simply when the thread on that connector saver starts screwing up, I just take it off, throw it away, and buy another one. I'll be dead by then. Maybe some of you won't be, but well, I'm not going to live to 100. I don't think so. I don't want to. What's the deal? Was it too much? Too much technical stuff? Too technical? Not enough technical? So, as I said, I'll send the slides out on PDF so you'll have a record. And if you guys want to come up later, we can go through and do some measurements here rather than try and do it over the camera. Seems so. Hi, I didn't get a chance to. What's that?
Say what we're going to do. What we're going to do.
You're going to give me one?
I'm going to give you these five.
Really?
To throw the numbers off.
Yeah. Thanks, Larry.
We'll give
You're going to give me a real one now. What kind of pie is it, Larry?
It's peach pie.
Peach. Oh, wow. From Atlanta.
Yeah, it's not from Atlanta. Like bus.
Yeah. Oh. Hopefully it was in a cool pack of some sort.
So we're sorry you folks attending tonight on Zoom. We're not able to participate in the raffle for the pie. Maybe somebody can take the pie and show it to the camera so they will know what they're missing. This is our Vanna White here. So is it showing? You see the pie?
You want me to stop? Sorry.
All right. So I can't pull numbers out because I have the so I'm going to ask Barb, did you? And so Kathy will have the tickets.